2, 1. Okay, so welcome in. Let's take a look at the extension of Bernoulli's equation to Bernoulli's principle. Okay, so that's what I want to be able to do in this video, and I also want to show you an example. Now, I'm not going to talk about Bernoulli's equation. If you want details on that, I'll put up a link up above there. Okay, I'm assuming that you have seen this formula before. All right. Okay, so the only thing that I'll mention with regards to this formula is that, okay, the terms that you see within here, so it's obviously worth knowing them. This is pressure. Okay, this is density of the fluid. This is the speed of the fluid, okay? And again, so density, this is gravity, and this is the height. And if you take all these three terms, if you add them together within a fluid, which is at steady state, and on the assumption, okay, that within the fluid flow, okay, so it's at steady state, the fluid is incompressible, so the density stay the same, okay? So that's number 2 that you have. And then finally, it's frictionless. So if you make those assumptions, we find that when we add up the terms, okay, these are constant. So that is Bernoulli's equation. Now, how does it relate back to Bernoulli's principle? So in Bernoulli's principle, really what happens is this term kind of drops off, okay, within here. I just want to be able to show you, why it drops off. Now, first of all, so if you take this, okay, and you take a look at this term, it has this particular h in here, which is actually height. So this is density, this is gravity, and this is height. Now, what height are we talking about within a fluid? So you might think, is this the depth within the fluid? No, it actually relates back to some kind of a gravitational, okay, height that we have. And this is really just a reference. So if you take a fluid, so let's say if this fluid is flowing over here, you can literally say that, okay, I will take this with respect to some reference. Maybe this is my height h is equal to 0. Okay, in here, and this would have been the actual height, okay, reference point h, okay, that I would have. And with respect to that reference, now I can calculate exactly what this term is. Now we set the h with respect to whatever, reference point we want. So this is really arbitrary and up to us. Now, if you take this and now all of a sudden, okay, so I'm just going to label these two tubes. Let's label this fatter one as 1 and then this narrower one as number 2. Now, if you can see this and this fluid is passing along here, so it's passing from 1 to 2, then what is going to happen is, okay, so this particular fluid is going to have a certain speed. Now, let's say this speed is, V1, and then let's say that this speed, okay, is moving at V2. Now, V2 is going to be faster, okay, than V1 because of the narrowing, okay, and that we know that we have the volume flow rate, okay, from the first tube is always going to be equal to the volume flow rate of the second tube. This is due to continuity, okay, the law of conservation, okay, within here of mass and the volume that flows from one and the other, okay. If you want, I'll put up a link up above there that just mentions volume flow rates, okay, within here. So you should understand what a volume flow rate is. Now, so you have these two particular speeds. Now, if you notice, okay, on the 1 and the 2, they're basically with respect to the same height, right? So here, okay, if you take a look, okay, and you take the average of the height, they're basically at the same height right here. And that actually leads us to Bernoulli's principle. So what Bernoulli's principle does is, okay, it says, okay, well, what do I know? I know that if I took the pressure, and this is going to be the pressure in that first tube, and I add it to 1/2 times the density. Now the density is going to be the same fluid that I have in both, so I'm not going to label them as 1 or 2. It's the same exact density that I have in there. And the speed, so here the speed does matter because the speed does change, so this is squared, plus, okay, the density times gravity times h. This is supposed to be equal to a constant, right? Which means that in the first tube, this is going to be equivalent to exactly the same thing as my second tube. So that second tube, that narrower tube, should say that I'm going to have my pressure, which is pressure P2, plus 1/2, okay, times the density of the speed. Okay, the speed is going to be faster because it's narrower in there, plus the actual density, okay, times gravity times the height. And as you can see here, these two terms, okay, are going to cancel each other because they're at the same height. And when you do that, when you do talk about a fluid and it's exactly at the same height under the same assumptions as Bernoulli's equation, what this is actually Bernoulli's principle. So what Bernoulli's principle nicely shows us is the relationship between the pressures that we have in one tube and the pressure, okay, in the other tube. And also, okay, it shows us the actual relationship between the speeds. So within here, so if I take this back in, so these two are equal to each other by Bernoulli's equation, and this is actually called Bernoulli's principle, right? When you're talking about exactly the same height. So within here, you can very clearly see that if you're going to have, because really the only differences between here, the densities are the same, right? It's the same fluid. So the only things that can change is pressures and your speeds. Those are the only two. And this really nicely captures for us that if we have the narrower tube, if this actual velocity, okay, goes up, right? We know that this one, okay, right here, okay, is slower than this one. Then if this is going up, then since the left-hand side and the right-hand side must equal to each other, then this pressure actually has to go down, okay, in comparison to this pressure over here. And that's a really nice thing to see. So if you notice, if you have one tube, okay, and the speed is slower than in another tube, then for compensation, due to the law of conservation of that energy, the pressures actually have to change. So you'll have that the pressure in one is going to be higher, and if the speed in the other one is higher than the first, then the pressure will drop. All right, so that's what happens. Let's take a look at this, okay, through an example. Now, before I jump into an example, I'll just kind of box this in, and you can jot down for yourself, this indeed is Bernoulli's principle. All right, so that's what we have. Now, let's use this particular principle to solve a problem. So let's talk about the same tube. Now I'm just going to give you some actual characteristics in here that we have. So we're told that in the first tube, so notice that the actual speed right here is 2.5 meters per second. Okay, the radius, so here if they give us the radius, so we're assuming that this is kind of cross-sectional, okay, of this whole thing. So that we have, so the radius is, it's kind of like this is the tube itself, right? So this is the radius of this right there. Okay, they give us the radius of the second one, so notice it's smaller. They also tell us what the pressure is in that other second one that we can measure. That's the pressure on the walls. And we don't know anything else. And what we're after in here is we want to find what the pressure in P1 is. So we want to find the pressure in here of the fluid in comparison to this pressure over here. Now, what do we know without doing any calculations at all? Well, so the things that we do know is, number one, the speed in here, which is 2.5 meters per second. Okay, in comparison to the speed in here, this speed in here is going to be much faster because of the narrowing. So that's number one, okay? So that's what we know. Let's find that particular speed that we have, because if we want to use, this is Bernoulli's principle. If we want to use this principle, okay, we're going to have to find all of these different items. Now, we're dealing in here, so notice that it mentions we have H2O, so this is water. So for water, okay, so our density for water, we'll assume, okay, so it's our standard density, which is 1,000, okay, kilograms. This is going to be per meter cubed. So that's the density of water. I kind of believe it was at 4 degrees Celsius or something around there. But that's what we typically assume if it's not given to us. All right, so we have the density in here. Well, that's one of the components that we have. We have this particular speed. We're looking for this pressure. right? We are told this pressure, so that pressure is right there. We can change that to pascals for SI units. We know the density, while we don't know this particular speed. So let's maybe start with that. So step number one, okay, is going to be, let's find V2. So what is my speed? Well, my speed comes from the fact that the volume flow rate from the first tube is going to be equivalent to the volume flow rate of the second tube, right? So that's what I have there. Now these two are, so it is the cross-sectional area multiplied by the speed is equal to the cross-sectional area of this speed. Now, I know what the areas are in here. So this is going to be pi, right? So this is, we're assuming that it's a tube which is circular cross-section. So pi r1 squared, right, times v1 is equal to pi r2 squared. And this is going to be times v2. So if I substitute all of the given pieces of information, so let me do that. The pi and the pi will cancel because they're both on the same side. The R1, you can certainly put it in metric standard units, okay, if you like, or you can keep them both. So it looks like they're in centimeters in here. So the reason for that is because you have them on both sides. But let's just, for consistency, and especially if you're a student and you're always kind of doubtful maybe, just put it in SI units. And then from there, you're going to be able to find what you need. So if I put it in SI units, so this is going to be 0.011 squared times V1, which is 2.5 meters per second. So 2.5, so that's all in standard units. Okay, on the second one, so this is 0.32. This is going to be small, 0.0032 squared. So again, I'm changing it to meters from the prefix. And then I just don't know V2. All right, so let's plug this into the calculator and let's find out what it gives me for V2. Here it is, okay? So it's about 29.541, etc. So I'll keep, a few decimal places here for myself, okay, with regards to the speed. And this is going to be in metric standard units. So now I have this speed right there. Okay, so now that I have the speed, I have the density, okay, in here. I guess the one other item, okay, that I have to be careful with is I do have to change this pressure to metric standard units. So, let's do that. We can use this, okay, as our guide in terms of converting it back. So this is just the regular unit conversion. So 1 ATM. And this is 101,325 pascals. All right, so that's the pressures that we have. So that's going to be 1.1 times 101,325. So that is my pressure. So it's quite a bit of pressure in there. So 457, okay, 0.5. I'm running out of space there. I'll just shift it over. So I have this, so 0.5, and this is pascals. All right, so now I have my pressure. Now, with all of this, let's try to write down the entire formula and then everything that's given. So let's copy this. Let's bring it down, okay, in here, and let's start filling out what we do know. So we're trying to find P1 plus. Now this is going to be 1/2. Okay, the density, which is 1,000 for water. The speed, so this is 2.5 squared, equals, now this is the pressure, so P2, which is 111,457. Okay, I think I'll just leave it on the calculator there. So that's 111,457.5 plus 1/2 density. So again, so this is going to be times 1,000. And this whole thing, I have to multiply by, this is going to be times 29.541, so times 29.541, etc., squared. So now, as you can see, all I have missing is that P1. Okay, so let's do that. Since I already have the right hand side pressure on my calculator, I'll do this calculation. So plus, okay, 0.5, which is the half, times 1000, and then multiplied by 29.541, and then squared it. Okay, close it. So that's my right-hand side. So it's quite a lot. Now you can certainly write it down. So 547,792.84, okay, 05. And now I have to bring this term over, okay, on the other side so that I can solve for the pressure P1. So that's going to be this, okay, which I have on my calculator, minus, okay, so whatever I have there. So 0.5 times 1000 times 2.5 squared, put it all in brackets, okay, equals. And notice this is 544,667, okay, 0.84, etc. Now this is the pressure. Now you can round. So if your teachers will tell you to round to something, it's fine, right? So I'm just kind of going to go back. It looks like the minimum amount of significant figures was 2. Okay, so I can certainly round this off to 2 sig figs. So this will give me approximately the pressure, which is 540 pascals. And that would be the pressure on the left-hand side of that fluid that you would have in here. So that's the pressure inside here. Notice the pressure in here is less, right? So it's quite a bit less than on the left-hand side. And the reason for that pressure drop is because the energy is transferred into kinetic energy of the motion, okay, of that particular fluid passing through. And that's exactly, okay, what happens in terms of the compensation. So you have two terms. You have a pressure term, okay, and then you have almost like a kinetic energy term in here. So if you're going to notice that your kinetic energy term is increasing, that means the pressure has to decrease, because the left-hand side and right-hand side have to balance. They have to stay constant by Bernoulli's equation. So that's a very nice example that illustrates this concept. It's a little bit of math, okay, and then solving for your unknown. But I hope that now you can relate back Bernoulli's equation back to Bernoulli's principle. So here you see Bernoulli's equation. So that's that. Okay, and then here you see Bernoulli's principle, which relates back to two different points, okay, of a fluid at the same height, okay, with a steady flow, okay, that you have in steady state, and what happens between the pressures between those 2 points and the actual speeds. So there you have it. Thanks for watching. I hope you found this video useful. Bye, everybody.